Hello, everyone, in what is hopefully the first of many such Ask Me Anything, and I'll perhaps answer anything that is submitted to me via a panoply of different options we have available to us in this digital age. You can leave me comments when I post a call for questions to be asked on my YouTube channel community page. That's Dr. Brian Keating. You can send me an email in my email list, briankeating.com/list. And you can join my Patreon. You can ask questions there, Dr. Brian Keating. And on my website, briankeating.com/podcast, you can leave a voice message. There's a tool there, a widget called SpeakPipe. But we'll take about 20, 30 questions from around these different places. Oh, Twitter is another place, Dr. Brian Keating on Twitter, where you can solicit my input on your most burning existential question. And I'll try to do this every so often. This one's actually a 60,000 subscriber celebration. Took me so long to record it. I actually am honored to say we're now over 71,000 subscribers on YouTube. Please do subscribe there. You can ask me questions, interact with these brilliant brainiacs, 14 Nobel Prize winners, 4 astronauts, 3 billionaires, 2 Pulitzer Prize winners, and many, many cool conversations coming up in the near future. We just had episodes with Sean Carroll and Sabina Hassenfelder, and some solo episodes where I do conversations about deep topics in experimental physics. And that's sort of becoming my niche, is to really steal the thunder in some way from my brilliant theoretical colleagues like Neil deGrasse Tyson or Sabina Hassenfelder, and do what they can't, exploit my unfair advantage, which is to do experiments in the laboratory and talk about experiments as an experimental physicist. That's my training. And we'll explore the universe of experimental physics on this channel more and more with solo episodes. And I call those 10-minute thesis projects. And I'm really delighted to be sharing those with you. We have one coming up soon about the most expensive water ever made and ever available, to me at least, in the universe. You won't want to miss that, so do subscribe to the channel. Those explainer videos are only available on YouTube. There's just no point in posting the audio only. But I hope you'll do both. Subscribe to the podcast and to the audio channel and all my other feeds. And sometimes I like to reward folks by sending you free copies of my various books. I've written 3 or produced 3. Losing the Nobel Prize, Into the Impossible, and also Galileo's Dialogue. So sometimes I'll give those away. Other people's books, I'll give them away. My friend Will Kinney, past guest on the show, I'm giving his signed book away, in Infinity of Worlds. So you can find out all that information on my website. I love to give back. I love to teach. And I love to do experiments and to tinker. So let's begin with Twitter. So as I said, I'm Dr. Brian Keating on Twitter. This comes from a friend, Jay Yao, the /engineer. He's a super producer too. In addition to Stuart Volcano, he works for the James Altucher podcast and the entire impresario that is James Altucher. What Jay is asking, my super producer buddy, who was a guest about a year and a half ago, he asks, is there life out there in the universe other than on Earth? What would it look like? Will they look like me? All right, Jay. I hate to break it to you. Maybe I don't. You're a handsome man. We've had shared meals together, delicious Chinese meals in the Upper West Side. They won't look like you, most likely, and that's a good thing, ups your dating probability. Well, first of all, we have no real evidence. We have no evidence for life outside the Earth. I often hear there's an abundant probability just based on discoveries from all sorts of disparate scientific directions, including the fact that the Kepler satellite has demonstrated the existence of thousands of planets around other stars. The James Webb Space Telescope not only just recently recorded the signature of an exoplanet, but also the fact that it had carbon dioxide in its atmosphere, the byproduct of our respiration. But none of that is evidence of life. That's the evidence of potential life. And it's sort of like saying, if I look out here in San Diego and I see the desert, there is a possibility of life. There are certainly life forms that live out there, but in any particular location in the desert, there have to be an incredible number of competing variables that have to all conspire to be in place in order for life, a lizard, a gecko, whatever. There has to be just the right properties for life to actually be there. It's not enough for life to potentially be there. And then the question is, will they look like you? I guess, partially that has to do with whether or not life is not only ubiquitous, but also technologically advanced, sentient, conscious, capable of building societies. We talked about this and an episode called, If Darwin Had a Spaceship. And that was with Dr. Eric Kirschenbaum in the UK. And he makes the point in his book that there's a tremendous number of things that we would expect to find in his book, A Zoologist's Guide to the Galaxy, including, if life does exist, that there would be a tremendous amount of culture and civilization required to support an advanced life form capable of communicating its existence to us, or even visiting us, or producing some sort of technology that we could see. So that is also a very high hurdle to pass. We had to just think about our space program and how many thousands, hundreds of thousands of people conspire in a good way to make that program a success. And in that sense, that requires that they have a common organization and a financial system, and they have a culture, and they have language, and they have mathematics, and all sorts of things. So that's a huge number of hurdles, and I'm barely scratching the surface. And that's once life exists, matures, evolves, and becomes sentient technologically, and is able to do all sorts of cool things. So short answer is very probably not. They won't look like you. It might have certain features that you have. But first we have to get to the point of whether or not life exists at all, and then whether or not that life could be technologically advanced. Thank you, my friend, for the question. Moving on. Reader 312. What is your most recommended book based around physics and engineering for a student that is going to university next year? Well, you're in luck, because just recently I did an episode with Sean Carroll. Sean Carroll has a series of books, the first of which just came out in September, called The Biggest Ideas in the Universe. And the first one's about space, time, and motion, which would be likely your topics that you would have to take in an introductory first-year physics class. I know that's certainly what we do here at UC San Diego, where I am a professor. And it covers a great deal of things, including the mathematical background, including calculus and some aspects of things like symmetry and other properties that are incredible to know about. And then it culminates with some really delicious red meat or white tofu, including things like black holes and space-time diagrams. It's an incredibly satisfying book. There are other books. Lenny Susskind has a series of books called The Theoretical Minimum. Those are more advanced, I would say. And Sir Roger Penrose has some books, The Road to Reality. These are more kind of synoptic overviews of all of physics from the laptop of masters like Lenny and Sir Roger, both past guests on the podcast. And we, have this notion that you can kind of pick up as much as you need to know, during the school year. But actually, it's much better. I always tell my students, you should really never have downtime. I mean, I command them, I don't command them, but I recommend that they only work 6 days a week, that they never, ever work 7 days a week, based on kind of the values that I have, to give yourself a weekly Sabbath and to relax and enjoy and not always be focused on work. Because if you are, you're kind of beholden to your job, or in this case, being a student. And I think that that's not entirely the best way to approach life. But that being said, the corollary to that is that 6 days a week, you should be thinking about your job or your work or your avocation in this case, and that'll be physics. So not only reading the stuff that is required reading, but going beyond it. And that will really tell you if you have kind of the desire and passion to continue through the really hard times, which you will encounter many times as an undergraduate and maybe eventually as a graduate student. For me, it was reading books by Isaac Asimov, science books, not science fiction, ironically. Ironically, I say, because I'm the associate director of the Arthur C. Clarke Center for Human Imagination here at UC San Diego. But I always gravitated towards his science-heavy books rather than science fiction. Same with Arthur C. Clarke. But I would read biographies of Feynman and of Einstein and the great scientist, and Carl Sagan, all sorts of my heroes. And then eventually Galileo, who is still sort of in my life, and he's on my desk over here. And you can learn a lot from the struggles, and you can actually get into people's personalities by reading a lot of history of the field. Books by Tim Ferriss, the astronomer, not the, kind of body hacker podcaster extraordinaire. So Tim Ferriss wrote many books. Coming of Age in the Milky Way was a great one. The history of science. So read on the non-technical kind of popular science front, in addition to, Losing the Nobel Prize and Into the Impossible. You should read some books that are technical, like either Sean's book or Lenny's book or even Sir Roger. But I really do recommend Sean's book, his new book. And in fact, although I had recommended in the past to Zev Weinstein, a friend of mine and son of a friend of the podcast, Eric Weinstein, I did assign him, so to speak, a series of books, including Lenny Susskind's, to get up to a level that he far exceeded my expectations of. So he's actually doing original research soon after kind of just devouring that series of books by Professor Lenny Susskind. So it may happen to you, but don't feel bad if it doesn't. Start off at your own pace. But again, the most important advice is to keep the curiosity up. I always say passion is like a spark, but the real fuel is your curiosity, because that'll keep you coming back for more, rather than just being inspired the very first time to pick up a book and, oh, maybe I could be like Feynman. And then we found out most of us can't be like a Feynman. Prometheus Warp X on Twitter. Again, these are coming from Twitter. Find me on Twitter at Dr. Brian Keating. What happens to space-time near an ultra-intense ion ring azimuthally accelerating towards c, the speed of light, while compressed towards zero radius? I have no idea. I'm sorry, Prometheus. Great name, great question, presumably. I think that this would take me so far beyond into a second PhD to learn about what is an ultra-intense ion ring, how do you azimuthally accelerate it towards the speed of light, and compressing it to zero radius. That would be a cool thing, but I have no idea what would happen. Question number 5, I think. Bob Kerbel on Twitter. Can you explain why a universe expanding at superluminal velocities would leave an imprint like the polarization of the cosmic microwave background radiation? Can you describe the measurement to measure the polarization? Well, in fact, I can, Bob. In fact, that's what I've dedicated my life to the past 20 years or so, all in pursuit of this, which I borrowed from Sir Roger when he was here, described in Losing the Nobel Prize over here. But I'm not one of those authors who says, if you want to know more, buy my book. I always hate that. I also hate when you go on a podcast and they're like, can you explain your book in enough detail and depth that my listeners of this podcast don't need to buy it? No, I won't do that. I didn't write it to make money, but I did write it to convey a message that needs to be revealed in accordance with the kind of proper background and the setting and the characters. I hope I've done that in my books, and I'll continue to improve, I hope. So what is polarization? First of all, polarization is the result of the interaction between light and matter. And what happens when light interacts with matter then determines its subsequent polarization state. So light generally can be unpolarized or polarized. When it's unpolarized, like light from the sun, it has no preferential orientation of the transverse waves that we call electromagnetic radiation. These are waves that oscillate up and down. Their direction or plane of oscillation of the electromagnetic field is what we call the polarization. So when light then interacts with a material, a medium, it could be a metal, it could be an insulator, a dielectric, it could be any sort of material you like, several different things can happen. Some of the light's intensity can be absorbed, some of the light's intensity can be reflected, and some of the reflected or transmitted or absorbed radiation can have a net polarization state accorded to it, meaning that you can have a suppression of one of the axes of polarization, leaving the reflected light to have a net polarization transverse to it. And that's what the basis of a polarized sunglasses are. So I've got my cheap homemade polarized sunglasses. And what they do is they suppress one axis of polarization. They transmit one and they block the other one. So 50% of light gets through, and these are sometimes used to suppress glare, and you can see it's sort of suppressing glare. But when I put two of them together, as I'm doing on YouTube, sorry, do subscribe if you want to see it, you rotate these at right angles to each other, they'll completely absorb, say, the light, or they'll completely transmit it with a 50% suppression of the intensity because it is absorbing and transmitting only one polarization. Where does all this have to do with polarization of CMB? Well, Bob's asking about the superluminal expansion. That's referring to inflation. So inflation is the hypothesized early evolutionary phase of the universe that kicked off the Big Bang that we know and love today. So it's not part of the original Big Bang. It is a later explanation to explain some of the lacunae, the gaps in our understanding of the Big Bang, including how did it start expanding in the first place? It should have contracted maybe to nothing, and we shouldn't even be here to ask questions about its existence. So it's a theory first put forth by Alan Guth in the late 1970s, early 1980s, that we're still trying to really prove. And it's a question of, can you actually prove something in physics? Well, the closest that we can have is have a tremendous amount of circumstantial evidence that would not prove inflation, but would rule out the alternative hypotheses. Those alternative hypotheses include Sir Roger Penrose's conformal cyclic cosmology, and Aegis's and Paul Steinhardt's bouncing cyclic models, and there are others, string gas cosmology, those would be falsified in a certain sense because the presence of inflationary perturbations to the space-time metric would cause waves of gravity, gravitational waves, that would then propagate through the universe, eventually causing a unique pattern of polarization of the heat that we call the cosmic microwave background radiation. And that's what the BICEP experiment was intended to do, the South Pole, and that's what we're trying to do with the Simons Observatory in Chile. And I have a lot of content about both of those, and I'll continue to do so, not the least of which because I think it's the most fascinating thing I can do as a scientist. So I hope you'll check those out and not hesitate from asking more questions in the future. Thanks, Bob. Back on Twitter, we have Ryan Hogan. He's asking, will there still be a debate if there's a hard problem of consciousness in 100 years? If no, who won? What happened? Well, I don't have my crystal ball. I do have a crystal ball. I keep it at home. But I don't know. This is a very good question. Of course, the hard problem of consciousness is a term coined by past guest David Chalmers, and that is whether or not one can actually explain the phenomenon of qualia or phenomenal experiences, experiences of what type of maybe sensory experiences and others. This is a hard problem between the physical phenomena, brain function, and actual physical function in the outside world, and whether or not other things, entities, could have consciousness as well. We talked about it. It's remaining a hard problem as far, predicting whether or not it will be answered, it will be solved. I just don't know. It's a little bit beyond my potential comprehension. And I do feel like perhaps we're in the phase of consciousness studies that, medicine was in when it studied, phrenology and leeches and bloodletting and so forth. So I don't know. I don't think anybody could say for sure if it'll be solved, because I don't think it's something that can be solved via mere application of thought or computing power, etc. Although some things might give us insight into the hard problem, simulated minds and things that pass the Turing test, or as Sean Carroll called it, the Keating test, whether or not a artificial general intelligence would commit suicide in our interview together. So Ryan, don't know. I think it's incredibly interesting. I think philosophers have come up with all sorts of ideas from, panpsychism to OR. Gravity plays a role in consciousness. It's an exciting field. I think I love to learn about it. Not the kind of field that I would get into, just because I like to actually be able to build things and tinker around and make progress on a human timescale, etc. Don't know, do care, and appreciate the question. Next Twitter question comes from Unknowable Sky. What a beautiful name. Is it true that the new dark matter-less galaxy would represent a significant evidence against Mond if it is true? How contentious is this new discovery in the astrophysics physics community? Can it be proven true? Thank you, Unknowable Sky. So you're referring perhaps to the video I did called This Galaxy Has No Dark Matter. And that we explored this galaxy found by Professor Peter Van Dokkum at Yale, which suggests that there is a galaxy who is being orbited by globular clusters, which I described in the video. And those globular clusters are orbiting around the galaxy, which is referred to by some huge long series of characters, A.E. Shaw-12S22. No, it has another name. We call it 1052, I think, in the video. And these globs, balls of stars, are orbiting around the galaxy. And that galaxy, just by its luminous matter alone, just counting up how many stars are in it, what it shows, it doesn't require any matter other than what's luminous to control and cause the gravitational motion of the globular clusters that kind of orbit it like planets around our sun or any other gravitational phenomena. It doesn't require any dark matter. That is a challenge for Mond. And I did talk to Mordecai Milgram about that in our conversation linked up here, which is called No Dark Matter. Unfortunately, I do apologize. That video had really terrible audio on Mati's side. I'm going to try to send him a microphone or maybe go visit him in Israel next year when I go back for my bar mitzvah anniversary. More details to follow. Maybe we'll plan a trip there into the impossible getaway. But the response that he has had is that it doesn't. There are certain kind of loopholes, I think would be one way to describe in the Mond theory, which don't require that all galaxies if they're independent, in other words, if they're not embedded in some larger cluster of galaxies or some dark matter halo, that they could be accounted for within the Mond paradigm. Whether or not that remains true based on, say, the more detailed studies that will come out, I think they could spell trouble for Mond. If, say, the Webb telescope doesn't need the globular clusters, which are farther away from the dark matter core and may or may not be the best tracers of the gravitational potential field of the galaxy, the Webb telescope will be able to zoom in and see the individual stars orbiting inside of the galaxy. And that will be a keener and more crisp test of the actual amount of luminous matter in that galaxy, because that's actually in the plane. And that's what Mond really talks about. Mond doesn't really have as much to say, in my understanding of it, about the globular clusters and things outside the core radius of the inner gravitational potential field. What Mond can do very well is account for the rotation curves of galaxies. And we've talked about that many times. I'm sitting in the office of Jeff Burbidge and his late great wife, Margaret, and they used to take images, and here's one of them, a plate from Mount Wilson, I think. It's older than me. These images were then used to take spectra. Here's a spectrum of a galaxy that Margaret took. You can barely see it. These are on photographic glass plates. So cool. It's a piece of history right here. And they then were collaborating and teaching a young Vera Rubin when she visited right here at UC San Diego back in the 60s, and they kind of inspired her to take up this rotation curve business in galaxies. And then she showed that galaxies have very flat rotation curves. And there was already evidence from Zwicky and others that dark matter was something to be taken seriously. So that will be the crispest test that could spell doom for Mond. But stay tuned for that. Hopefully that'll be coming soon. This one is right up my canal. No, it's actually not up my alley at all. It's from James Aragon, who asked, could a canal from the Sea of Cortez to Laguna Salada, could that help reduce droughts and lower temperatures in the Colorado watershed? I have absolutely no idea. I don't even know this was even thought about. We do have a giant salt lake here called the Salton Sea, which is a manufactured, man-made lake. But that was really meant to divert water from the Colorado River, cause a lot of tension. It's horribly polluted, although it's getting cleaned up. It's kind of a cool area of Southern California to visit in the winter. Don't go there in the summer, you'll die. So I don't know. It's a question for another podcast. But I guess I did say ask me anything. Okay, now we're going to YouTube, answering some questions. And you can ask me questions there on my community tab, which you can get to on a phone or a computer, but not on an iPad for some reason that I don't understand yet. But maybe one of my YouTube engineer friends will be able to explain it to me. The first question comes from Floyd Aldrich, who's a member of the channel. Thank you, Floyd. That means he supports it financially at something like $5 to $10 a month, and that really does help to cover some of the many expenses. I do operate at a loss. I don't like to take video ads on the podcast. I find them a little bit disruptive. Sponsorships, not saying I always will have that position, but for now I don't like it. There's enough ads on YouTube as it is. I have YouTube Premium, which is gladly funded by people like Floyd and the many dozens of members that pay a little bit each month to support the podcast. You can also do that on Patreon. I have a similar number, a couple dozen supporters over there. And you can also super follow me on Twitter, apparently now, for about the same amount. Give priority to the folks that are asking questions from those different venues. Floyd asks, I know light can't escape a black hole, but how fast would something have to go to escape? Well, that's kind of the point, is that to escape means that in the future, you won't be inside the black hole's so-called event horizon. And what Sir Roger Penrose proved in the 1960s that led to his Nobel Prize was that there's no such thing as a path within the black hole's, once you get within the black hole's event horizon, that doesn't include a future event where you encounter the singularity. In other words, your world line will start to converge no matter how much speed you have. And the more speed you have, the kind of faster it will take for you to get to the black hole singularity. That's the kind of frustrating thing. The more you struggle, it's like the ultimate quicksand. You'll never be able to escape, no matter how fast you could go. And I don't know about tachyons and things that are faster than the speed of light. I think those are pretty fanciful. There's no evidence for such things. So it's not possible, unfortunately. So stay away from it. You'll get more than just spaghettify. Next comes from Shweta VS. Could you please tell us more about the three main approaches to relativistic gravitation theory, or your views on it? Thank you. So there are many different so-called theories of everything that attempt to unify the laws of quantum mechanics, the laws of nuclear physics, the laws of electromagnetism, with the law of gravity. Those go under the rubric theories of everything. And in theories of everything, one encounters very many interesting phenomena, such as the fact that we have no incredibly small microscopic scale behavior of quantum mechanics that is compatible with gravitation. In other words, we have infinities, we have singularities that emerge when you get to, say, the core singularity of a black hole. So for that reason, we don't have really a current understanding of how gravity can be reconciled. There are approaches, and Sweat is talking about those. Those sometimes include geometric theories that attempt to bind together various group structures in the same way that we bound together the weak nuclear force with the electromagnetic force, so-called SU2, cross U1 symmetry. Those are group theoretic manifestations, and those might be quite good as well. They might be the right approach. Of course, string theory is another approach to unification of gravity with quantum mechanics. But, my thought is that we really don't have a good grand unified theory where you unify together the strong force with the weak force and the electromagnetic force. There is no such current present theory that is really accepted for that. And it's not for lack of trying. So I always joke we're putting the toe, finding the theory of everything, ahead of the gut. So that can always be a fraught proposition. And I feel like more flowers should bloom than are currently blooming, but there's no real telling right now. In fact, string theory is kind of undergoing a dark ages, an anti-renaissance. I don't know how to describe it. Where people are really pessimistic about it. That doesn't mean it's wrong. We don't appeal to authority on this podcast, but we've talked a lot about it. And then, of course, my friend Eric Weinstein's, his theory of everything called geometric unity, which is another type of geometric approach. There's past guest Garrett Lisi's approach. There's a completely different type of approach by Steven Weinberg, which involves these kind of graphs, these game of life type structures that we've talked about on the show together as well. And maybe it's time for an update with him. I've done more on the kind of geometric front with Eric and Garrett and others. Maybe it's time for an update on the computational complexity side of things. Thank you, Sweta. Still on Twitter, Chanik says, when will you have Lex Friedman on your show? Thanks for everything. Thank you, Chanik. Well, I'm hoping that Lex will be on my show when I go back on his show. So I've invited myself back on his show, and he enthusiastically accepted for round 2, which he calls a round 2. And I said, what I really want is to have you on my show, and people are demanding it, like Chanik and many others. So hopefully that'll happen late this year, early next year, whenever our schedules and stars align for a trip back to Austin. And Lex has really upped my game since I was on his show the first time. We'll put a link to that over here. I was on his show. It's got about 1.4 million views so far. It's 4 hours long. So if everybody watches it, let's say half the people watch it all the way to the end, everybody watches it halfway, then you're talking about 3 million hours of very fine television. But let's just say, what's 3 million divided by 168? So that's how many weeks worth. So that's 18,000 weeks of somebody's time has been watched on this. How many days is that? Let's do that really quickly. Now we're talking 125,000 person days have spent watching me and Lex jabber. And get ready for a longer one. We actually recorded for 5 hours when I was on the show the first time. He had to trim it down. I think it came out great. It's got thousands and thousands of thumbs up and comments, and I try to read them every so often. So thanks for that question. Short answer is I'm going to bring my microphone and turn the tables on him. He's aware of it. Lex, game on, brother. LV Gamer Cats, beautiful name. Dark Matter Armand. Which one do you think the universe picked? That's a very good question. I've spent a lot more time thinking about particulate dark matter in the form of particles, than Mond. Although, Mond has certain attractive features, and some people, like past guests on the show, Sabina Hassenfelder and Stefan Alexander, have models that are quite, attractive. They have a lot of fascinating, aspects to recommend them. I don't feel, though, that it's conclusively possible to say whether or not it will be one or the other. In fact, it could be both, right? It could be that some aspects of Mond do obtain and some aspects of particulate dark matter do obtain. It could be some, phase transition in matter that it obtains of ordinary matter. These are all really fascinating things, different possibilities. So I wouldn't say now. I have a lot of kind of familiarity that could occur with my experience in the cosmic microwave background experimental field, where we're actually doing very similar types of low temperature physics with detectors and readout and data acquisition and data analysis techniques. These are, some of the most fascinating things I think that one can study. So, from my perspective, I think the jury is sort of still open on which of the two would be right, but I'm fascinated to find out more. And I just happen to have more familiarity with the particulate searches, the direct detection searches. That doesn't mean they're right. But it is fascinating to think that maybe there could be a confluence of these things, and we could have, kind of the best of both dark worlds. Okay, I hope you'll continue to submit questions to me and these future Ask Me Anythings. This one was supposed to come out months ago, but due to my sloth and so forth, I've tarried long enough, and now it's time to put it out there and answer your burning questions. Flor Horabecca, I think is how you pronounce it, says, I have a bunch. Perhaps you can choose which is least ridiculous. Number 1, if we reverse the first second of the Big Bang, we see the electromagnetic and weak nuclear force merge. If merge is the right word, we say they separated. But is separate the right word? Yes, in some ways they become different manifestations, different incarnations, just like solid, liquid, and gas phases are different phases of water. There's one underlying material, water, and it changes its phase and its behavior as it is cooled or warmed, in this case, going backwards in time. So yes, I think that's the right word, separation. You have phase separation when it comes to things like water, liquid, and gas, and you have phase transitions as the universe goes from being perhaps a single force described by a single force, namely the theory of everything, gravity plus the strong and weak nuclear forces and the electromagnetic force. And then as it cools down, as the universe expands and cools, those forces fracture off and take on unique identities that don't allow them really to be perceived as a single entity anymore. So going backwards, it's sort of a form of unification. Going forward, it's a form of separation. So yes, I think that's fine. Okay, Jimmy Jazzy says, what's your favorite thing in mathematics? Is mathematics invented or discovered? I think the answer to the second one, it's both. We do discover things about the universe, but we also create things about the universe. Now, those are true and they exist whether or not we describe them or not. But when you think about the actual practical application of mathematics, say calculus was invented in a sense by two different mathematicians, Leibniz and Newton. And it was invented for a particular purpose, and then it was discovered that it had application to the physical world, namely that Newton's laws could be very accurately modeled by calculus. So I think it's both. Of course, it's an eternal question. Nobody really has the right answer to it, but that's the way I think about it. Blake Lyon says, now I'm reading again from my YouTube community page, Blake asks, in what ways is it accurate or inaccurate to think of galaxies as giant solar systems with stars orbiting massive core areas instead of planets orbiting a star? It's a very good model in a lot of ways. And in fact, that model is not terribly inapplicable to even an atom. Bohr received his Nobel Prize for basically a planetary model of the hydrogen atom. And so it has a positive descriptive power, and therefore it's useful. It can allow one to calculate many different properties. In the case of the solar system, though, it differs in that 99.8% of the matter in the solar system is contained in the sun. Our galaxy has far, far less contained in a central point, which is maybe arguably Sagittarius A star, the supermassive black hole at the center of our galaxy. That is a physical point, and it is true, mathematically speaking, the stars are orbiting around that point at the center of the galaxy, but it's not orbiting because of the gravity of the black hole. That black hole is pitiful mass comparison with the total mass of the galaxy, which has several hundred billion solar masses as compared to 6 million or so solar masses worth of mass in that black hole. So it's massive, certainly. And the objects that orbit around it do behave. They have certain properties that are Newtonian, but to accurately describe them, you need to use general relativity the closer they get to the black hole. So close in, the approximation of calling it a solar system is perhaps less precise, but not really less accurate. We need to describe the orbit of the innermost planet in our solar system using general relativity, and that's Mercury, which led Einstein to come up with the theory of general relativity. So it's a very useful model. It's, of course, the galaxy is not a perfect plane, neither is the solar system, nor is it true that that all the matter in the solar system, nor all the matter in the galaxy is visible matter that can emit light on its own accord and be detectable. So yeah, it's useful. Of course, they're quite different in a detailed level. Thank you, Blake. Another one taking me far, far out of my comfort zone into the impossible. Sean Mitchell asks, what do you think of the postulation that the universe is a fractal pattern hologram made tangible by interacting electromagnetic fields, and that the only two things that really exist are light in many evolved forms and consciousness? I have no thoughts on this. I never heard such an expression. Fractal pattern hologram, don't really know what that is. And tangible by electromagnetic fields that really exist, I'm not sure what that means. We know that matter exists. We know that light is just one form of energy in our universe. Consciousness, see above, we don't really have a model for how consciousness emerges or if it really emerges. Some say it's an illusion. Some, like past guest on the show, Nick Bostrom, claim we're living in a simulation at a certain level. So no. We do have another question about fractals from Shweta VS. What exactly is fractal science, and why do we see fractal patterns all over nature in the universe? So it is true. We have fractal behavior on the largest scales in the universe. The distribution of large-scale structure in the universe traces a fractal-like pattern with fractal dimension. So what is a fractal? Fractal means fractional dimension. It is something that doesn't have a neat integer dimension like a line or point or even a sphere or cube, etc. So it has an in-between dimension. And we'll put up some illustrations of various fractals. The Mandelbrot set is one. The Lorentz attractor is another. What is the dimension of them? What is the dimension of the coastline of California? It's not a line, because if you zoom in farther and farther, you get a longer and longer coastline. That doesn't happen for an ordinary line. And so these are famous problems. Fractals manifest themselves in the behavior of certain functions that describe complex phenomena. Not complicated phenomena like building a microwave telescope. It's not complex in that it has sensitivity to initial conditions and so forth. It doesn't. You start off, you have the materials, you build it, and it works. It's hard as hell. Take it from me. And my students and colleagues are the best in the known universe at doing these things. But it's not complex. You'll get the same result every time, in principle, if you follow the same instructions, just like solving a puzzle. But puzzles can be really complicated. But a fractal depends very sensitively on where you start. And of course, the famous butterfly effect, coined by James Gleick, who maybe I'll have on the show someday. The butterfly effect being the thought being that tiny perturbation of a butterfly in Australia flapping its wings would later cause a tornado in Texas. We don't have such fine-scale modeling that actually proves that such things occur. And in my conversation with Tim Palmer, who's a co-recipient of the Nobel Prize, the Peace Prize, for his work on climate change, he and I discussed this very effect. And in fact, it's the core theme of his book. And more interesting, maybe even than all that, as interesting as that is how do we understand the transition from the classical world, which has things like chaos and weather and fractals and so forth, to the quantum realm, where we don't have like fractal behavior per se, but we have entanglement. And that was really fascinating. I refer you to that conversation. Hopefully it'll be out very soon. And you'll enjoy that. That's based on his new book called The Primacy of Doubt. James Rushineski asks, what is needed for people to move to Proxima Centauri system? So are these some like annoying neighbors, James? I mean, you got to fill me. Who are the people we're talking about? Who do we want to get rid of here? Gotta be careful about that. So for people to go to Proxima Centauri would be quite a ways. Proxima Centauri is the nearest star system to the Earth. It even has an exoplanet that's orbiting around called Proxima Centauri b that could even be, similar in some ways to the Earth. So to move there would require that we get there. So Voyager's moving really fast, fastest thing ever made by humans. So it would take 26,000 times the time that light would take to get to Proxima Centauri b. So you're talking about 100,000 plus years to get there. I don't think people can ever get there. Now, if you're traveling at the speed of light, then of course time gets dilated and you don't experience that time. But if we're just talking about what would it take now, it would take 100,000 years. So don't get your hopes up. I don't think Bezos or Musk, either one of them, is really too keen on selling trips to that deep in outer space. Although Richard Branson, I don't know, that guy's kind of crazy. He's thinking that he can make a huge business out of suborbital spaceflight, which we achieved back in the 1960s, and he wants to sell rides for $250,000 a pop. It's a pretty expensive way to brag to your friends, right, at a cocktail party. So I don't think it's in the cards. Let's work on Mars first. Maybe that'll be more practical, if such a thing could even be called practical. Joseph Rapp asks, what is the evidence for and against a multiverse? Well, there's no evidence for it. Really, there's no data that suggests it. There's a possibility one could obtain data for it if one were to observe sort of patterns of interaction of our cosmic microwave background that would be reflective of an encounter with another universe. And at the encounter point, this globe over here, imagine it crashing together with another globe like it. Well, where they intersect, those two regions of the two different disparate universes in the multiverse would share properties. And so therefore you could expect to see the impact surface between those. And maybe the manifestation of that would be a circle. If you take two spheres and smush them together, the border of the boundary where they overlap is a circle. So people have proposed, Latham Boyle and others. And I did a video about this on the solo episode side of things, 10-minute thesis side of things. And you can find that evidence, for a multiverse. So we haven't seen it. Short answer, spoiler alert. Against a multiverse, also hard to really say that you can't have a multiverse. First of all, there are many different, incarnations of the multiverse. The simplest one could just be to say that there are regions of space-time inaccessible to us at the most rapid possible speed, meaning that we can't interact or communicate with regions of our own universe because they lie outside of our causal horizon. That's the simplest level. And then it could go all the way up to every mathematical structure exists in a universe of its own, like Max Tegmark has talked about. Or it could be that there's different universes in terms of their different physical properties, the different laws of physics, different physical constants, different speeds of light, gravitational forces, electromagnetic charges, strength. So we just don't know. But I think it's fascinating to contemplate them. One thing's for sure, if we do discover that inflation took place, there'd be a lot more evidence for it. In this book, of course, which I'm going to give away on my website, signed by the author, Will Kinney, An Infinity of Worlds, is just about that. So here, you get the actual signed copy. When you subscribe to my mailing list, you go to my website, you'll find giveaways galore, so enter those and you'll be entered to win this book. It's really hard for me to ship these things around the planet. So I really only can ship to my friends in the United States of America. But I'm planning to go to Europe next year. I've been invited to go there for various events. So maybe I'll drop some in the post. I'll post them when I go there to England, Italy. I'll keep you guys abreast of that if you subscribe to my mailing list, which I'll put the link here right below. And that's very simple. That's just briankeating.com/list. And you may be entered to win some upcoming space swag. Could be a meteorite, could be a Nobel Prize. But I'd have to steal another one from another laureate friend. Shweta VS asks again, with regard to baryon symmetry. When the universe was created in the principles of symmetry, there should exist equal amounts of matter and antimatter. Both should annihilate each other, and ideally there would be nothing. We now know there's a violation of that symmetry. My question, what is the reason matter is preferred over antimatter? Another phenomenal question, Sweta. We don't know. The universe has a tiny broken symmetry. And without it, we wouldn't be here to ask the question as to why there is a tiny asymmetry at the part per billion level. In other words, for every 1 billion and 1 protons in the early universe, there were 1 billion antiprotons. And those folks annihilated with each other, and what was left over were 2 billion photons and a single proton, a single particle of matter. And we don't know. We know that ratio exquisitely well from observation of the CMB and other corroborating pieces of evidence from Big Bang nucleosynthesis. But we don't know why that is. There are many different people working on this, and there are certain conditions that need to be in place in order for this symmetry to be violated. But I always say, we talk a lot about symmetry and how important symmetry is. I mean, Noether proved a very famous theory that relates symmetric operations with conserved quantities like energy, angular momentum, linear momentum, but we don't know why they have applicability. But also, it's when the symmetries get broken that things that are interesting occur. The Higgs boson mass mechanism is only possible because of a broken symmetry in the quartic and potential of the Higgs boson. So we don't really know why that is, but lucky that it is, or else we couldn't be here to ask and hopefully answer partially some questions. Okay, I'll go back to Twitter with my friend Tyler Goldstein. He says, if you could change something to improve the education accreditation system of academia, what would you change? It's a very good question. I think about this a lot. Are we essentially in a Hunger Games in academia? Have we effectively closed the door to really the level of success that was present and possible just a few decades ago when I was becoming a professor? The odds are so much harder now to get a faculty job. And I used to compare it to, say, getting into the NBA or let's say the Major League Baseball here in America. We have this farm system where there's single A, double A, triple A. There's also a new one that they added, like A plus or something. I don't know. Anyway, let's say there's 3 levels: single A, double A, triple A, and then there's the major leagues if you're really good, right? So I kind of made the analogy between undergraduate, graduate school, postdoc, and then faculty. I'm not comparing any of those. I'm just saying, in terms of the statistics and the odds to get from levels to levels, it's much harder, I think, to get from, say, undergraduate to graduate school than it is to get from single A baseball to double A baseball. And it's certainly extremely hard to go from triple A baseball, which in this analogy would say being a postdoctoral research scientist, into becoming a faculty member. That's really hard. That would be major leagues. In fact, it's so hard that every single slot we have for a professorship here, and this is true across all the comparable R1 top tier universities like mine, and even some of the, not R1 schools, but even further down the line, teaching colleges or whatever that don't do research. And the odds are 400 to 1, which is harder then to get into. In other words, you have a higher probability of going from AAA to the major league than you do from going to be a postdoc to being a faculty member, and then getting a grant, and then getting tenured, and then winning a Nobel Prize, who knows? Those go down exponentially. But the difference is that it is hard to become a postdoc, but there's many, many more jobs. One of the problems is there's far more jobs to be in the AAA system analogy than to be in the Major League Baseball. So we have this surplus of incredibly brilliant people that have good jobs, that have good awards and honors, but they're not permanent. The academic environment does not confer a permanent position to a postdoctoral scientist. It's kind of the stepping stone where you learn how to build out your own lab, you build it up, you study under another professor or under their mentorship, and then you become a mentor to your own postdocs if you get a faculty job. But it's incredibly hard, and it's one of the things I don't know how to address. It could be that we have too many postdocs, and it could be people in the faculty realm need to stop encouraging so many postdocs. And then the question is, well, if you don't have as many postdocs, then you shouldn't have as many graduate students. So maybe we should have fellowships and encouraging them. And I think the answer is that we need more faculty. And I'm not saying this self-interested. I'm already tenured. I have an honorary chair professorship. It's not self-interested for me. We have this enormous institution with an enormous brand. And all these colleges that I work with, the best schools in the universe, and literally I work with people, very close colleagues, on every one of the 6 continents where there are universities. And I'm trying to start one in Antarctica. Next time I go down, I'll do it. So why don't we have more professors? Well, we don't have room for students. We've kept the student to faculty ratio for decades. It hasn't grown. It hasn't kept up with inflation. The number of slots has gone down. I remember getting into Brown University and being overjoyed and thinking that was great. Now it's basically impossible to get into Brown. I mean, you have to be, so incredibly off the charts with extracurriculars. Forget about, grades. In some cases, the grades are less relevant. And it's sort of become a purview of alumni and maybe donors in some cases. And, that's less common at a state school like UC San Diego. But we have incredibly hard and competitive admission rates. Across the UC, it's only like 12%. When I was a kid applying to college, Harvard was like 8%, 9%. Now it's 3 or 4%. So it's gotten incredibly out of control and very hard to get in. And places like MIT or, Harvard can brag that they turn away, 9 Harvards a year. In other words, there's kids good enough to go to Harvard or UC San Diego, and we turn them away. And in California, at least, we do have a mission to serve in the public school system, to serve a certain number of in-state students, which the other schools don't have. And so for that reason, we're more diverse. We have more kind of socioeconomic diversity because we can't really discriminate against people based on income or ability to pay. It's really, are they good enough? Do they meet the prerequisites or not? So it's been frustrating. So short answer, increase the number of slots. Now, the tuition has increased faster than the rate of inflation or the rate of growth of the universities. We've grown at 2% or 4% maybe in California across the board for how many undergrads we admit. Inflation, the prices have doubled in 20 years, and the tuition and fees and so forth. And I know that's true at private schools, maybe even more so. And the faculty really haven't changed that much. So the faculty are kind of growing below the rate of students. So in other words, we could solve a lot of things. If we had more students, then we could justify more faculty, which would then justify more postdocs, which could then, or this, maintaining the level of postdocs, but increasing the percent that become faculty from 0.25% to, something more manageable, like 2% or something. It's not an easy problem to solve. And then you have to battle with, well, where do you house these students? And do they need to be on campus? And I think there's a lot of room for things that could be taught off campus that don't need a physical campus to do. You don't need a physical campus as much in an English class as you do in a laboratory science like physics or engineering. And so could have a hybrid scenario where, we do some teaching offline. I've been doing, some Zoom still, even though I'm teaching in person again. But anyway, long-winded way of saying we need to grow faculty, which will eventually grow the number of faculty just by having more supply and even just keeping the demand the same. Okay, last question from Twitter for this inaugural Ask Me Anything comes from my friend Martin Bauer, professor in the United Kingdom. What is your prediction, he asks, for the Simons Observatory measure of the Hubble constant? I think, it's dangerous to predict, what you're going to see in an experiment, as you know, Martin. But I would think that since Planck and WMAP are in such good agreement, those are two other CMB experiments, spaceborne experiments, ACT and the South Pole telescope are also in large agreement with the measurements of Planck and WMAP. It would be, just from a Bayesian perspective, I would expect that we would measure something on the lower side, closer to those values, but we never know. I'm more interested in kind of you and other theorists and other experimentalists and observers like myself. How could we explain it? I'm always of the mind that we want to use as little magic as possible, despite the opening line of the podcast, but read by Sir Arthur C. Clarke, that any sufficiently advanced technology is indistinguishable from magic. I would love to have as little magic as possible, meaning that we don't have to appeal to some strange new force field or dark unseen component. I'm actually, most intellectually kind of attracted to an explanation that involves magnetic fields and primordial magnetism. I did a video about that called Hubble Crisis Solved with Magnets, a fascinating kind of conjecture of how early magnetic field energy has just the right properties to produce a very rapidly expanding early universe that then, can decay in a certain sense. And so we could measure a higher Hubble constant at later times with the optical type experiments and a lower Hubble constant at the early times from the CMB. My friends have worked on that. And that video is there for you to check out and see what you think and give me feedback on that. I guess I should also check Instagram. You can find me there. Guess what the moniker would be? Dr. Brian Keating on Instagram. Being on Instagram, I'm not as attracted to it, or Facebook, as I am to the Twitter or the YouTube community page. So that's usually where you'll find these solicitations for you to ask me anything. One comes from Andy Oates, who's a very good friend of the podcast. I'm surprised he didn't write me on YouTube, but instead wrote me on Instagram. Do you think the American government is right? Period. Then he says that UFOs are real and we are being visited by people not of this world. Well, Andy, I don't know if that's what the U.S. government is saying. I am a very big skeptic about UFOs, but I'm an optimistic skeptic. In other words, I hope that I'm wrong. I think there are people that don't want to change their opinion, that believe that there are no such things, that this is all, fiction, figments of imagination, that these objects are, easily explained in other ways. And then there are people that, think that they're totally real and guaranteed to be there, and we should pay very strict attention to them because this could represent, a threat or, something incredibly interesting to know about. I would like nothing better, as any scientist would, to actually make contact with another civilization, because we'd be able to get an actual maybe level jump, a level up to physics of the 25th century. This would be amazing. And any scientist worth his or her salt should kind of endeavor to be excited by that subject. That being said, we have to ask if the current level of evidence rises to the occasion. And a lot of what I've seen has to do with, and I've talked to many of the people involved with these things, CIA operatives, to people like Tom DeLonge, who's involved with his own project, to the Stars Academy, Mick West on the opposing side, who believes that everything can be explained, and does a good job at kind of providing evidence at least against the interpretation that these are extraterrestrial. So I don't think the U.S. government has any position on it. I think it is of interest to people like pilots and military, because if it's not of this out of this world, it could be a threat to our national security. Although I have to say, given how badly we blew COVID and even things like the Ukraine invasion, we have these $1 trillion 3-letter agencies like the TSA and the NSA and DARPA, I guess 5 letters, and all sorts of other agencies, and we failed to even diagnose, the problem with COVID was coming to our shore, and at some level represented a huge threat to our security. I knew about it, thanks to a dinner guest in January of 2020, what China was doing, and building hospitals in 8 days that can house or imprison 1,000 people. These are things that we should have known about. If I knew about them from, someone at a dinner on a Friday night, certainly we could have gone into mass production of masks or, hand sanitizer, all the things that we ran out of, toilet paper. Thinking back now, it's astonishing. The fact that we had some sort of a treatment, vaccine or not, depending on your perspective, that we've had these vaccines for a while. Maybe we could have had them earlier. And maybe they wouldn't have been as politicized. And maybe we wouldn't have had these economic shocks that then caused us to have to invest trillions more, or spend, I'll say, trillions of more dollars. So how did we not catch that if the government is so good? And so you have to ask, if they're suppressing information, how come they're so good at doing that? This conspiracy is so effective at suppressing knowledge of actual alien beings, but so ineffective at dealing with the most basic functions, sort of keeping the lights on, keeping us safe. That's the main role of the government, in my idea. Okay, I can't resist answering my friend Jeremy, who goes by the name of Alien Scientist, big YouTube channel, the same name. He asked 3 questions. I'm going to answer one of them, which is, what are your opinions of the Galileo project? And Avi loves theories on interstellar objects. So I have Avi on multiple times in the podcast, at least 3 or 4 times. He's a friend. I actually volunteered for Project Galileo to be on their external advisory committee. I did that for about a year. I didn't really do much, but to be honest with you. But, having some level of accountability, I thought would be a good thing. And, what Avi's doing now, I think, is pivoted away from, focusing, no pun intended, on Oumuamua, this object, and more on other types of objects and future objects that might be discovered, including this so-called, I shouldn't say so-called as a pejorative, this interstellar meteorite, which has been confirmed, which is he's going to lead an expedition, privately funded expedition. It's good to be at Harvard. And he's going to go scuba diving in Bali or wherever this object is. Now, I kind of gently chided him back when he and I chatted in January 2021, when his book Extraterrestrial came out, about his conviction that Oumuamua really was real as an extraterrestrial visitor, an object, a technological relic of a distant civilization, not of our solar system. And I said, Avi, if you really believed in this and you did have access to the billionaires that you do have access to, why don't we go and catch up and lasso Oumuamua, rather than sending tiny little spacecraft as the Project Starshot that he was involved with and co-leading to Proxima Centauri B. At best, we have some information from Proxima Centauri B in 50 years, whereas if we caught up, with the same type of cameras, caught up to Oumuamua and landed on it and maybe captured it, put little thrusters on it, did our best Bruce Willis imitation, that's in our solar backyard compared to Proxima Centauri B. Furthermore, we'd get information back, more or less immediately because it's still heliopause of our solar system. It was traveling very fast, but it's not fast as the speed of light. So that being said, I wondered about his conviction. At that time, he said to me, well, with the Vera Rubin telescope and other instruments, we'll be seeing, 5 of these a week or something once that comes online. And, I just had to think, well, there's a lot of things that are likely that never pan out. In physics, there's a saying that, 99% of 3 sigma detections are wrong. And, they should have a probability of being wrong of, 0.4% or something like that. What if they don't? What if Vera Rubin, we're just unlucky and these extraterrestrial garbage barges, they didn't send out a salvo of them, or we're not able to see ones that come as close as this one did. It was on my birthday about 5 years ago in Hawaii when it was spotted. So, he didn't seem to agree. So he's obviously moved on, again, no pun intended, from Oumuamua and is on to other things like this meteorite that fell to Earth, maybe digging out. I think that's going to be maybe harder than going to Oumuamua to dredge out a couple kilograms of meteorite in an area of the South Pacific Ocean. I think that's going to be a challenge. But if anyone can do it, it is Avi. And for now, like I said, I really enjoyed it. I hope you guys enjoyed this first ever Ask Me Anything. Maybe we'll do it again when I hit another round number of subscribers. Please do subscribe to the YouTube channel, which is Dr. Brian Keating. Twitter, Dr. Brian Keating. Instagram, Dr. Brian Keating. You can leave me a voice message anytime at my podcast page, which is listed on the screen. First, I should say sign up to my mailing list, briankeating.com/list. That is listed for now. And let me type in my podcast website where you can leave a speak pipe, a voice message. I listen to every single one of them. Can't promise I can answer every single one. As things ramp up, I get busy teaching this coming year. Got a bunch of brilliant new graduate students, undergraduate students, hiring a new postdoc soon, going down to Chile soon to work on the Simons Observatory. That'll be fun. Then traveling to Europe, as I mentioned, next year, maybe Israel. So a lot of fun stuff coming up. We have interviews with people like Will McCaskill, who's written a wonderful book about philanthropy and the future. Huge #1 bestseller around the world. Our past catalog is unmatched with folks like Sean Carroll and Sabina Hassenfelder, Eric Weinstein, Jim Simons, the late great Freeman Dyson, 14 Nobel Prize winners. And I love to do it. And on my YouTube channel, exclusively, I do videos about explaining experimental science. That's where my unfair advantage, my niche is doing experiments, analyzing experiments, thinking experimentally, and teaching you. People always say, oh, I'm no Einstein, I don't want to be a physicist. Well, Einstein was an experimentalist. And even good old Albert made a lot of blunders, as you know. He wasn't perfect. But even if he was, you don't have to be him. You can be you, can do stuff, and anybody with an interest in taking things apart and solving puzzles can be an experimentalist, a tinkerer. You were all playful as a kid, every single one, even you theorists. So I want to explain how these experiments work, what the cool aspects of them are, how do we interface and learn about experiments and use them to learn and refine our knowledge about theories as well. And that's my mission. So I hope you'll join me, join my various lists and so forth. And until next time, wishing you a magical rest of your week. Signing off, yours truly, Dr. Brian Keating.